Oh, hi. So yeah, I'm from Warsaw, from a beautiful country of Poland. I don't speak Belarusian well, so this will be a talk in English. Okay, can you hear me well now? Everyone in the back? Okay, that's great. I'm a software developer. I'm really flattered by the invitation to speak at the Minsk Jack. I hope that you will enjoy my talk as well as enjoy visit in your country. This will be a live coding session. I'm not a slides guy, hence this is the only slide that I have. I work at Pragmatic Coders, where I develop a D2C investment platform for a British market. And yeah, in the past I used to lead Warsaw Jack, but this is not as interesting as the reactive stuff, I guess. Since this will be a live coding session, it has to run on some stack, and it will be all Spring. So it will be Spring 5, Spring Boot 2, release candidate 2, released yesterday, just to make it a bit more challenging for me, I guess. And it will be Project Reactor as well. But this doesn't matter that much, because I don't want to focus on Spring way of doing that. It just Spring make it super convenient to show you what I want to discuss, because it gives a couple of nice abstractions. But I will try to go a bit deeper. So if you, for example, prefer to use RxJava instead of Project Reactor, we will focus on stuff that is common to reactive approaches. So if you strip off the APIs, then you will basically know the most basic building blocks. And having said that, let's remove the slides. And although we will speak about reactive programming, we will start with something completely non-reactive, something super boring that you probably are used to, just to, first of all, be on the same page and to also have something to compare to. So what we have here is a simple application. It just listens for one GET request. And within this endpoint, what we basically do is sleep for 1 second and then just return some value. All of the examples that I have will be simple, but I hope that they will be expressive, and they will require a bit of imagination. So treat this sleep as some blocking operation. Let's call it a database call, calling some downstream service via HTTP, reading data from file, doesn't matter. It's just a blocking operation that takes 1 second. It always takes 1 second, just for the simplicity of the example. So we have no caching, the operating system is not helping us, none of such stories. And having said that, I have a first question to you. Knowing that the blocking operation takes 1 second, what will be the latency of that endpoint from the client's perspective? 1 second. Yeah, but that would be my answer as well. But we will try to be good software engineers, so we will measure instead of guessing. So let's run this service and let's measure. Maybe let's make this a bit bigger. Let's hit it. And it's a bit more than 1 second, but only for the first call. For the second one and all the consecutive ones, it will be a bit faster. Just for the first call, it takes a bit longer because we need to bootstrap the application. And in this presentation, we will make a couple of semi-benchmarks. Those won't be proper benchmarks. We won't warm up the application properly. We just don't have time for that. So what I would like you to focus on is not the concrete values that we will get here, but rather rough values that those numbers oscillate around. So Let's say that it's not 1 second and 18 milliseconds, it's just 1 second, for just the sake of example. Okay, so knowing that we have a latency of 1 second, I have another question to you. Imagine that we have 5 concurrent users of this application hitting it at the same time. How many TPSs, transactions per second, can we get with such an implementation? 1? 5. Okay. You're too fast, but yeah, I would also go for 5, but we're trying to be good software engineers, so we measure instead of guessing. Maybe let me tell you what's going on here. We're basically running Siege, which is a benchmarking tool. We are running it in a benchmark mode with 5 concurrent users, and we're doing 5 repetitions of those calls just to get a bit more trustworthy results. And we can see that we are getting HTTP 200s and more or less 1 second latency for those calls. And we can see that we are able to get close to 5 seconds. So, sorry, 5 transactions per second, 5 TPSs. But let's make it a bit more interesting, although one of the answers was already given here. What will happen if I'll raise the number of clients to 16? What would we expect to happen if we run the benchmark?
Less than 16, a little bit.
Yeah, because of this answer, you already know what will happen. But I would expect it to be 16 TPSs, but as you already know, this won't be that much. We will get less than that, and you can see that based on the latency of those calls. And we're getting only 8 TPSs. But why? 8 cores. Okay, so yeah, we have 4 CPUs, but on hyper-threading. But this is not that part. But this will come useful at some later point of time. But yeah, clearly we have some kind of a bottleneck here, and you're going in the right direction. It's related to threading, how many threads we have here. And I have done here something nasty. For the demo purposes, I just set the number of worker threads to 8. If we remove it, if we rerun the service, obviously we will get close to 16, I hope. Let's measure that. But looking at the latency, we can tell that the results will be better. And yeah, we are close to 16. But let's say that for some reason we want to keep this limit of 8 worker threads. But we would like to still be able to get reasonable TPS rates. So what could we do to stay at those 8 worker threads and achieve 8 TPSs? Can you speak a bit louder?
Maybe we should walk
In
in parallel, no?
parallel, yeah, but we have those 8 worker threads. So going parallel is right direction, but we need to do it in a bit different way. Like what we need to do is move this blocking operation to some other thread. Yeah, so from servlets 3.1 specification, I guess, something that is really, really old, like it's 8 years since it was released. We have the asynchronous processing capabilities. And we'll use that. So let's try to move it out of the worker threads. We will use abstractions provided by Spring so that we don't have to code directly to servlets, because there would be a lot of boilerplate code here. So let me just up. Let's rerun it. Still, we have this limit of 8 threads. Let me check. Yeah, we still have it. But I hope that this time we'll be above those 8 TPSs. So let's rerun our benchmark. And yeah, although we have only 8 worker threads, we are able to achieve 16 TPSs, which is the theoretical maximum that we can achieve with this implementation. And what's happening under the hood, due to the abstraction that Spring provides, basically this callable of string is under the hood using the asynchronous processing capabilities from servlets specification. And it solves our issue, but I would say that it does it partially, because there is an important part missing here. This part is that we do not control the threads that we move this blocking operation onto. So we cannot control how many of them we have. Basically, we get either none or everything. So is it possible to gain control over those threads? Yeah, it is. Otherwise, I wouldn't be speaking about that. But it gets a bit more technical. We create a thread pool that we are managing, so we have complete control over it. We can cache it. We can say how big it is, how big the queue behind it is. We have, but the purpose of this controller that we had, like previously, it was straight to the point. We exactly knew what's happening there, what business logic we are executing there, and right now we have a rather bad ratio of signal to noise. Like there's a lot of technicalities here. There's not enough. The stuff that we want to achieve here is buried somewhere deep down in all of those technicalities, under those completable features, asynchronous executing, setting the result into the deferred result. It's not something that I would like to have in my business application, because it's too hard to tell what is the purpose of this application if you have to go deep down into the technicalities. And can we do a bit better than that? This is the part where we can start talking about reactive. So let me go back to the previous version. I will use the best practices. I will copy code. Sorry for that. I will shortly tell you why. Previously, what we were doing, we were running a classical servlet-based application. So we had all the tomcats and so on there. Here we will use Spring 5 web flags. So I just copied this code just to have all the dependencies pulled in. And we will make it reactive. So instead of callable, we will return a mono. Mono is a reactive producer that is capable of producing 0 or 1 value. So we either get nothing or 1 value here. And let me return a mono from this callable. And let me run this service. OK, and we will execute a benchmark for it. Let's say for 16 users. It's running on different port. So what kind of value are we expecting here? Like reactive, so it should be super fast, blazingly fast. I would expect to be that way. And if we run it, it's not fast, definitely. We will get a terrible result. I guess you can smell the question. Why? Yeah. And I will wait for an answer. Only 4. No, this time I haven't done anything like that. It all runs on default, so no traps this time. You've already seen the answer, although it wasn't obvious. And it's something that you mentioned in the beginning. We only have 4 cores. And part of the answer is here. Usually you see here like Tomcat started on port or Jetty started on port. It's because previously we were running on a servlet container, so thread per request model. This time we are by default running on Netty. At least Spring Boot does it by default. And Netty is not a servlet container. It's a blazingly fast networking, asynchronous networking framework. But in order to utilize its capabilities, we need to write proper code. And we've done here something stupid. Because Netty runs on event loops. And we have, by default, as many event loops as we have cores. And this is OK. This is a really good decision, because you want to fully utilize those event loops. So having more of them would mean more context switching and things like that. So we have only 4 event loops, and we've done something terrible here. We've blocked on the event loop threads. Because we have only 4 cores, we got only 4 TPSs. So we need to do the same thing as we've done previously. We need to we need to move this blocking operation into some other thread. But the difference is that this time we'll have full control over that without having to spread it out, spread it with all of those technical boilerplate. So let me show you how to do that. The only thing that we need to do here is to tell on what threads, what thread pools we will execute this logic. There's an operator subscribe on here, and most of the reactive implementations provide similar operators. And they use so-called schedulers. To simplify it a bit, you can treat it as a thread pool. You can create a scheduler from an executor service. There's a couple of predefined ones, like immediate, meaning the same thread that we are on, parallel, so as many as we have CPUs, single, which is self-explanatory, and elastic, which means as many as we basically need. So for the demo purposes, this is OK. In production, don't use it. Always like limit that. But nevertheless, let's rerun the service. Let's execute the benchmark, and let's talk what is the difference here. So not htop, but siege. And as you can see, like the response times are OK, and we got 16 TPSs. Like more or less. We haven't warmed up the application. and we have full control over those threads. So what reactive implementations are giving us is the simplicity, ease of use, and safety of parallelizing our computations, moving them to other thread pools. This is something that really simplifies writing code that doesn't run in a single thread. But this is not the only thing that reactive implementations are giving us. So I will move to another example, unless you have some questions around this one. If not, nevertheless, after the second example, we will make a 10 minutes break, I guess, because this is a longer presentation than the previous one. So Sergey asked me to do a break in the middle. So let's move to another example. And this time, again, we have a rather simple application. It doesn't return a mono. It this time returns a flags. A flags is a reactive producer that is capable of producing any number of values. So it can be 0, 1, 2, 5, 550 millions, an infinite number of values. It just produces values. What we are doing here is each second we are emitting an increment, auto-incrementing integer. We take first 9 of them, and then we map them to documents or something like that. And this is another part that needs your imagination. Let's treat those documents like, for example, huge PDF files. So let's say that this document is a 1 gigabyte PDF file, and we have 9 of them. And what are the problems with such an implementation? Well, maybe let me show you how to use it, and then we will talk about them. So we are running it with time to. I haven't run it. Okay. So we are running it with time to get the notion of how long it took, and we are piping it into JQ to just pre-print the JSON. And yeah, let's run it. So we hit the endpoint and we wait. And we wait. We have 9 documents, each generated each second. So we wait, and after 9 documents, we get 9 gigabytes of data. An array of 9 documents. And what is the problem with such an implementation? So first of all, because we have to serialize into an array of those documents, we need to be able to fit it on the heap. So on the server, if we have 9 documents, each of them of 1 gigabyte, we need 9 gigabytes of heap just for the sake of serializing the payload, plus the heap to run the application. If we would have 10 documents, that would need to be 10 gigabytes of heap for the payload. If one of the documents was bigger, then again, bigger heap. If we had 2 concurrent users asking for those documents, again, so in the era of microservices, cloud computing, like this is a huge amount of heap. So this is one of the issues. The issue is that it's super easy to get out of memory error with such an implementation on the server side. But this doesn't end on the server side. We can have a huge server with vast amounts of RAM, but our clients, they might not have. So unless they are aware of it and do some tricks around that, they will inevitably hit out-of-memory error on their side. So we have out-of-memory error issue on the server side. If the server has heap big enough, we have a huge probability that the client won't have it. And another issue that is there is that this first document, it was generated after first second. However, to start delivering it to the client, we needed to wait for the all documents to be generated and serialized and sent to the client. Hence, ignoring the network bandwidth and latency, we needed to wait 9 seconds to get the document, the first document that was generated after the first second. So can we do a bit better?
Yes.
That's a correct answer. How?
To send the documents one by one and maybe to organize a kind of web socket that to take when document is ready.
Exactly. So what we need to do is change a bit the way we serialize things. Now, this will look like a bit of magic, so I will just do it, show how it works, and then I will explain what's happening under the hood, because it's, again, abstraction, like a contract provided by Spring. So instead of serializing to JSON, we will serialize to stream of JSONs. Let's rerun the service. And let's hit the endpoint. This time we won't parse the JSON and we won't need the time here. Let's hit it. And the thing that's happening is rather obvious. Instead of an array of all the documents serialized, delivered after 9 seconds. Each second we are serializing a single document and we start delivering it to the client. Does it solve problems for us? Yeah, some of them, but before we get there, let me explain what's happening there. Because we only change the media type here, and like magic happened. It's not magic; it's contract of Spring. Under the hood, if we hit this service, after each of the documents is emitted, like the first document is emitted, we serialized only this one document. And we flash the response buffer, so bytes start flowing to the client, but we don't close the connection. Another document is serialized, is emitted, so it gets serialized, we flash the response buffer, we don't close the connection. After all of the documents that we have here are serialized and delivered to client, only then we close the connection. So something that you probably heard about a couple of times, like this is an old idea. I remember doing similar stuff in 2009 or 10 using Comet by You. Although it didn't work as smoothly, it required a lot of boilerplate code and a lot of hacks, frankly speaking. And it worked on some browsers, on the other not, on some servers, or on other not. But what the reactive implementations are giving us here is the way to build abstractions on top of them that make it super convenient, super easy, and is battle tested by someone providing those abstractions. And does it solve the problems that we had? To some extent, yes. On the server side, we don't need to have a heap to feed all of those 9 huge documents at the same time. We only have to have a heap large enough to hold only one document at the time. So we need 1 gigabyte heap for the payload, ideally. On the time to deliver the first document, we again have the problem solved, because after this document is emitted from this producer, from Flux, we start serializing it and sending to the client. So ignoring network latency and bandwidth, after 1 second, we have the first document. After 2 seconds, we get the second document, and so on and so forth. And we are left with the last problem of out-of-memory error on the client side. And whether it's solved or not, it all depends how fast the producer is, so the server side, and how fast the consumer side, so the client is. If the client is faster than the producer, we have this problem solved, as long as the client has 1 gigabyte of heap for processing this, this document. If it's as fast as the producer, well, we again have the problem solved. However, if the server emits those documents faster than the consumer is able to process them, then maybe we have this problem solved, maybe not. It all depends on how much of a heap we have, how much slower we are. And there is a buzzword that you for sure heard about, like it's always mentioned in terms of reactive thingies. It's called backpressure, and it solved that that problem, but not on not if you use HTTP. At least if it's HTTP 1.1, because it's a protocol request response, so you don't have any communication in between between the server and the client. So for that, we will have another example. You, of course, have some backpressure that you are already familiar with. It's on the TCP level. But it's not an application level in the OC stuff. So to discuss backpressure, we will move to the application that is not a web application. But before that, I would like to ask you whether you have any questions related to this example, and whether you want a short break right now or after another small example. Yeah. So yes and no. Mono and flags are coming from Project Reactor, which is created by Pivotal, guys that also created Spring, or rather are hosting Spring and created Spring Boot. It's just another project. Simplifying it a bit, it's an alternative to RxJava. And what we are using here is Spring 5, the web flags, which is part of the Spring 5, which is a reactive HTTP component. So it provides us with a contract that says whenever we return a flags or mono from here, we will do some magic under the hood and do, for example, this part with the streaming. Any more questions? Okay, so... Okay, so we don't need break. We can go to another example then. And this time, it won't be a web application. It will be a standalone application so that we have communication between consumer and producer. Let me just run it to show you how it works. And the important part here are those colors. So we are starting processing some document on the yellow bar, and on the white bar we say that we processed the document. And the implementation, it's again trying to be reactive. We have a document repository. Under the hood we have 9 documents. Just for the sake of example, we read those documents from the repository, and we are returning a reactive producer here. So again, we're using flags. So we a producer that is capable of supporting backpressure. And then we subscribe to those emitted documents. On each of those documents, we log something on warning level, just to let IDE color it for on the yellow bar. We then sleep for 1 second to simulate processing, and then on log info, so on the white bar, we say that we're done. And the subscription here happens in one thread, or rather it's sequential. Hence, if you take a look here, everything happens on the main thread. And this will allow us to play a bit with the backpressure story. If you've heard anything about backpressure, then most probably you've heard the definition that backpressure is a way for a consumer to tell a producer that he's too fast. This is a huge simplification. I will make another simplification, but a bit more concrete. Backpressure is a strategy of dealing with too fast producer, and telling him to slow down is just one of them. There are a couple of strategies here. We can buffer things when the producer is too fast. We can say that we will drop anything that we were unable to process, or that we want to only keep the last value that we weren't able to process and drop everything else, or that we will just throw an error that we are unable to keep up with the rate of events. And hearing that definition, you for sure know that we have two parties here involved. We have the producer of events and the consumer of events. And in between, we have a protocol that allows them to speak to each other. And we will start from the consumer side, just to get the feeling of the protocol. So let me just simplify things a bit for now. So we'll move this logic to a class, or actually I already have the class written. So yeah, let's rerun it, and let me show you how the implementation looks like. So we have a subscriber that extends some provided by project Reactor basic subscriber, and we have an extension point who connects, which basically allows us to tell what will happen when we want to process the document that was produced. And we're just subscribing here. We are making here a little hack because we're returning here a mono. You shouldn't write like that production code, but this is only for learning experience. So keep that in mind. It will allow us to do a couple of cool things shortly. But if we run this service as we did, we can see that it's still working as it used to. So let's try to play a bit with this implementation. Let me just get familiar with the new keyboard here. Okay, we will extend one of the other extension points. We will implement the hook on subscribe method. But before we will do that, let's take a look how the default implementation looks like. So by default, in this hook on subscribe method, we are requesting for some large value of events, large value of documents for long max value. Although this is not a huge value, this is a special value. It's a so-called unbounded request, which means, hey, producer, give me everything that you are able to produce. So let's play a bit with this. With this, we will replace that with calling, for example, for one request on subscription. Anyone want to tell what will happen when we ask for this one document? Anything will change here in how our application works? Yeah, exactly. But let's rerun it. So what's happening here? Instead of asking for every event that the producer is capable of producing, we're telling to him, hey, Emit, give me the first one. And then we stop. We can, of course, ask for 2 documents, for example. And in that case, we'll only get 2 documents, and that's it. But that's not a way to implement backpressure. We could do that in the same way using limit, or take first 2 documents. So how could we make it different? We can extend our logic so that after processing the document, we can request for another one. And here we will be back to the way of working of this application as we started with. So we get first document on the subscription at the subscription time, and after we process the document, we are asking for another one, and so on and so forth. Now, I've told you that this is not the way to write production code this way. It's because it allows you to do nasty tricks, because subscription by default should be sequential, and what we can do here is parallelize it and do tricks like that. So on subscription, we are asking for 1 document, and then after processing it, we are asking for 2 more documents. And if we rerun this, we will hopefully see that we are processing 1 document, and let me get this a bit bigger. So we asked for first document, we processed it, then we asked for 2 more documents. And after processing each of them, we are asking for 2 more. So from 2 requests for that, we get 4 more, and so on. So we'll basically go exponential with that. But knowing that, we can start looking at some other ways to define subscribers. So let me create a different subscriber. Let's use a batch subscriber. This is again a class that I've implemented, and this time we will ask for batches of 2 requests. How it looks like under the hood. First of all, on subscription, we are asking for 2 requests, and after we process both of them, we are asking for 2 more. So what should happen? We will be processing 2 events, then another 2 events, and then another 2 events. So we're doing that in batches of 2. However, this is again only for learning experience. You shouldn't most probably do things like that, because most of the reactive implementations come with a lot of operations that allow you to do that. Like, for example, buffer, that allows you to do the same logic that I have done, the whole class, with just a single method call that is battle tested, done by the specialists that know a lot about threading. And yeah, we use their atomic integers, so it should be rather safe, but it's easy to make mistakes in those kind of code. So we should use what the libraries are providing us with. And this is a huge topic. This is something for another talk or two, the operators that are there. But whenever you want to write a subscriber, just check whether there's not something that is already implemented that you could reuse. And with that example, or rather with that part of the example, we know how the protocol or part of the protocol between the consumer and producer is. So instead of asking for everything, we can, for example, change it to asking for small batches or concrete number of documents. But the producer needs to be able to understand this, this protocol. And we are using here Flux, which is a producer that is capable of understanding it, but it also has to play with it, because understanding is one part, implementing it properly, or rather supporting it properly, is another thing. So we will move to the second part of this example, to the producer part, and we will play with three producers. We will start with the JPA producer, and we will try to tell whether this producer supports backpressure fully. Like, it doesn't mimic that it supports, but it really does so. So we will try to test that, and we will run the application in the debug mode. It's not as scary as it sounds, because it will be rather a simplified debugging session. To check whether the producer supports the backpressure, I usually write a test like that and put two breakpoints. The first breakpoint is at accessing the repository. So when we are issuing the call like a query in terms of JPI. And then I place another breakpoint when we subscribe to each of the events. And let's run it in debug mode. I will shortly tell you why we are doing it this way. Okay. So any questions in the meantime? Something hanged? The ID died, or the laptop. So you have to help me with questions. I will try to restart or do something else.
If you have questions, you can just take a microphone.
Okay, I guess it's back.
Okay, fine.
Okay, something temporal. But if you have questions, I will happily answer them. We're using JPA right now. We'll dive into it shortly, but this is a good question. So why do I run it in the debug mode? Well, not to debug, but look at the heap. So in my IDE, I open the memory view tab, and the first breakpoint here is only to take a snapshot of heap. Okay, a snapshot of heap. And then when we move to the subscription point, when I'm processing the first document, I would expect to have only one document there, not the whole, whatever is in the repository, but only the documents that I need to process. So I would expect to have here only 9 documents. But what I have here is only one document, but what I have here is 9 documents. So everything that we have in the repository, we have loaded onto the heap. So this is not an ideal situation. I wouldn't say that the JPA repository is fully supporting that. So let's take a look how it's implemented under the hood. So from what you can see here, it's unable to fully support backpressure because we load the whole repository, all that we get from the repository, we load onto the heap into a list, and only then from this list we are creating this producer. So we already have everything on the heap. And when we talk about JPA specification 2.1, there's no easy way to go around it. For JPA 2.2, which is already released but not yet widely used, there's a method that allows to ask for a stream of the results instead of loading that into the list. So let's take a look how it might look like. I want to run it on JPA 2.2, but instead I will stay on JPA 2.1, but switch to another implementation. I will run it on Hibernate, and Hibernate is using plain Hibernate instead of plain JPA allows us to use everything that JPA provides us with, plus the stuff that Hibernate adds to that. So let's rerun our debugger session. Hopefully this time it won't hang as it used to do previously. Or it will. Okay. Something weird happening, sorry for that. So we have a first breakpoint only to get the snapshot of the heap, and let's go to processing the first document. And we can see that we only have one document on the heap. One was added from creating the snapshot. If we resume the processing, so we will go to processing the second one, we can see that on the heap we have two documents, and just one was added, and so on and so forth. So for when we start processing the third event, we will have three documents on the heap. So this this implementation provides full or semi-full support for backpressure protocol. What one might expect in this implementation is to at some point garbage collector would kick in and got rid of all of those documents that were already processed besides the one that is currently processing. But for sure you know that this won't happen because those are JPA managed entities, so garbage collector won't be able to GC that, and for that we will shortly jump to the lower level implementation. But before we do that, let's check two things. First is the implementation of this repository. So let's check how Hibernate does that. I'm using here a deprecated version, so just it only looks like a JPA one. So what we are doing here is we are unwrapping Entity Manager just to use the Hibernate one, not the JPA limited one. And then we are asking for a stream of those documents. And from this stream, we create a flags, so the producer that is capable of supporting backpressure. And important thing is that we also say what to do on termination. So whenever we run out of documents to publish, or when there's an error thrown at some point of time, we just close the results stream so that we don't leak resources, connections, and so on and so forth. And as we've talked a while before, this is as good that we are getting only enough documents that we need to process, but we don't get rid of them. Like they are not garbage collected. So to do that in similar manner, we need to go a bit deeper. So we will do that on the JPA level. However, before we do that on the JPA level, I will show you one interesting thing. Because what we are doing here, we are logging every query that Hibernate is issuing. And if we take a look at how many queries we are issuing, we can see that when we ask the repository, we are issuing one query. This is a select all query, and this is the last query that we are issuing to Hibernate. So although we are getting results one by one, there is only one query executed. And to discuss how it's working, let me go to the JDBC implementation. Let's rerun the service. Maybe this time without the debugger, so that the IDE don't hang. I don't know why it's happening, but and it's working as it used to previously. JDBC repository is more bigger in implementation, so I will go through what's happening here. So when we ask for all the documents, we are getting the connection from the data source. We set auto-commit to false, so that, for example, we can use DB cursor or things like that that would allow us to fetch documents one by one. Then we create a statement. We set the fetch size so that we can deliver those documents one by one or two by two, so on and so forth. And then we execute the query, and from the result set, we create an iterator from which we create the flags. And again, we specify what to do when we terminate. So when we run out of results or there's an error, we close the connection so that we don't leak connections. Transforming to iterator is straightforward because the result set tells us whether there's a new document. So it's basically if true, return true. If not, then false. And close connections if necessary. But the next method is a bit more interesting because this is where we are doing something that Hibernate gives us out of the box. We are turning the plain result set into our domain object. So we need to use the low-level things like get int, get string, know what are the columns, what is the order, and so on, so forth. So as you can see, the JPA implementation is not easy to generify. Hence, for example, Spring data is doesn't provide reactive connectors. It does it for Mongo, Couchbase, and other NoSQLs because they have reactive drivers. JDBC is a blocking specification by design, blocking implementation. Hence, the generic implementations are blocking as well. There is work going on alternative to JDBC that is reactive, or rather not reactive, that is non-blocking, but it's still early in implementation, so don't expect it in Java 10 or even 11, I guess. But with this implementation, you can more or less see how it's working under the hood, or how you could implement that under the hood. Of course, it's not fully reactive, because still you have a driver that is mostly blocking in terms of relational databases, because only, I guess, PostgreSQL and MySQL have asynchronous drivers, and they are not yet as stable or fully featured as the old blocking ones. Yeah, don't treat it as granted. But the moral from this example is that you cannot be reactive only on one end, and hence the title wasn't Reactive Services, but Reactive Web Services. To fully utilize the benefits of reactive implementation, you have to be reactive all the way down the stack. If you are just reactive on your repository level, well, you are not fully benefiting from that. And if you are reactive only on like the endpoint level on the other end of the stack, again, you are not fully utilizing the possibilities there. And those are those three examples that I had here were to show you what kind of problems the reactive implementations are trying to solve. Of course, those are not all the problems that are there that reactive implementations can allow you to solve. Those are just the most important ones. Other importance are that such implementations allow you to create more resilient services because of going asynchronous, utilizing messaging or event-based workflows more. They make code way more readable due to those operators that, well, there's a plethora of them. Like even for flags, if you take a look at how many of them there is, it's an infinitely scrolling list. Like there are those basic ones like maps, flat maps, limits, and so on, but there are more sophisticated ones like buffer, window, and many, many others. And with that, I would like to thank you for listening to this talk, and I will happily answer all of the questions that you will have.
Yes, thank you, Kamil. Does anyone have questions?
There's one in the back.
I see.
I'm interested in your actually production experience with reactive libraries, exactly with Flux. Why you prefer exactly Flux instead of usual RxJava, and most suitable user cases in your life of reactive programming as trees call microservices in production and or so on. I mean, exactly in production.
Okay, I will answer the first question, and the second you will have to repeat because I don't fully get it. Why I was running on Flux, so Project Reactor, instead of using RxJava, observables, and things like that. It was only because it's from Spring and to have a consistent stack, because if you you can return a mono here, and Spring takes care of everything. You can also return in RxJava 1, this would be observable, as far as I remember. But in Rx Java 2, there are actually two producers there that are a bit more concrete than Mono, because Mono can be 0 or 1 event. In Rx Java, you have a single that will be always 1 event, or maybe that will be 1 or 0. So this is a bit more concrete. And for sure, you can do it by returning Mono and having here this, for example, single and converting it to Mono, because there is a lot of cooperation between guys from standing behind Project Reactor and Rx Java. There's one super smart guy, David Carnock. I guess I pronounced it badly, so David, don't kill me. That was one of the core developers of Rx Java, and still he is, but he's also doing a lot of Project Reactor stuff, and they are doing that to the extent that they are sharing a lot of operators. So under the hood, map, flat map, and so on, they are using the common code. Like they've extracted that to the library. And as far as I'm aware of, but I'm not 100% sure, you could return a single here, or maybe, or observable, flowable, whatever you have from Rx Java, and Spring will by default take care of it. And if it doesn't do that by default, you just write a converter, and there are methods for Mono to observable, or yeah, you can transform it to future, to completable future, and there is similar to single. I guess that for flags, there should be an to observable. It's not. So it's either called differently, or there is somewhere in the API a method that allows you to just convert flags to flowable, or flowable to flags. There are methods there in Project Reactor. Yeah.
Thanks. I understand. They have compatibility level with Rx Java. Yes. Second question is about your user experience in production with Reactive Java. I mean, exactly what's the issues in your life, your coverage with Reactive Java?
Okay, so I don't use in production all of the things that I have shown you here, because Spring Boot 2 is to be released next week. So I use it in stuff that I write on my own. It's not on the production that is working on clients with multiple users. I plan to do so on the whole stack. However, on production, I have implementations that are using parts of that. So it's not, as I've said, I'm not benefiting, taking full advantages of reactive programming, because I have endpoints that are not reactive, don't return streams and so on. However, on the lower layers, I'm doing that for parallelizing stuff, for accessing repositories, not relational, but those that provide reactive drivers, and it's working flawlessly. However, there's one thing that is super important here, and if you give me a second, I can briefly talk about it. I guess I don't have the code yet added here, but let me just quickly check if I have it.
Maybe we can check it a little bit later.
Okay, so I will just mention it. So what you are doing within those implementations is you are oftentimes switching context, like going from one thread to the other. In a lot of cases, this is transparent to you. However, under the hood, you are using stuff like thread locals, for example. You might not use it directly on your own, unless you, for example, write multi-tenant applications, which usually under the hood use inheritable thread locals. But a lot of stuff that you use thread locals, like session-related stuff is held in thread local. Transaction-related things are held in thread locals. If you use, for example, MDC, map diagnostic context from your logging libraries, you're under the hood using thread locals. And because here you are changing threads, those thread locals are not being copied, so the data is not going with your processing out of the box. Of course, you can implement that on your own, but it's not as simple and beautiful code as here that you just say, copy that, and that's it. It's a bit more involved. There are libraries that are doing that. So, for example, Sleuth is doing that for Zipkins, logs, and so on. But you still need to wait for transactions. Yeah, this is a long answer to this question.
Okay, thank you. Let's ask two more short questions. Two more short questions because we will give discount, 50% discount to the best questions. Yes.
Thank you, first of all. And I have a question. You showed us some benchmarks at the first part of your speech, and we saw a benchmark with 16 customers. And do we have a dependency of a number of customers? And what is the difference between old one when observable, something like observable, and the new one like Flux or what? And if we will increase the number of customers, for example, at 1,000 or even in millions, what will it be the difference between old one and new one?
Okay, so in the old implementation, you are basically utilizing thread per request model. So you have a limit here, and you can have as many concurrent clients as you have threads. So you can, of course, do not set a limit, but that would be stupid because then your application at some point would crash. So by default, Spring sets it to 200 worker threads, and you can only have 200 concurrent users. If you go asynchronous, then you control it by setting the thread pool limit. If you go to Reactive application, then you have only as many. You can, of course, run it on servlet containers, so you can run it without this subscribe on and utilize the thread per request model. And you can use the event loop-based implementation like Netty, and then you have one thread per each CPU. But this logic is moved to some kind of a thread pool. So you have threads processing those blocking operations. They are mostly waiting, but you set a limit here. Like this time, it's not limited because this is good for demos, but you should do that, like creating that from executor service that you, for example, that you said, I want a cacheable thread pool of 10 threads or something like that.
Okay, thank you.
Yeah. So if there are some cases when I could, for example, create a reactive service and which corresponding with some other service by the MQ, like message queue, any of them, and connect it to the monolithic servlet-based application. Maybe you know some examples from your life experience.
So messaging is asynchronous by default, by design. You can, of course, make it synchronous, but this is like rather a hack usually. And if you want to turn it into like messaging, if you have a properly designed, implemented application, you just replace the endpoint that you exposed with a listener that reacts to messages instead of reacting to HTTP calls. Whether you can afford for that or not depends whether you control all the consumers. So if you do that within your, if you control everything, you can do that. If it's a public API, then you will have clients relying on HTTP API exposed, so that might be tricky. But this is usually a good idea if you can do that. Of course, some flows would need to be blocking, so then staying on the HTTP is also a good decision sometimes. It all depends.
Okay, thank you for presentation, Kamil.
Thank you very much.